Hello everybody, in this video we're going to be introducing the concept of a system of equations in two variables, okay? So a system of equations in two variables, a little bit different than dealing with just one equation in two variables, but we're going to be dealing with systems of linear equations in two variables, so equations that when you graph them they look like lines, okay? So let's go ahead and start with the form that they come in typically, okay? So this form up here, of course, if you're like taking notes, you would want to write this down, but we say a system of equations has more than one equation involved. So you'll see here that I've labeled the first equation here, equation 1, and the second equation, equation 2, but we say they come in standard form, okay? So any form would be like ax plus by equals c, where all of our variables are on the left side of the equation and all of our constants are on the right. And the second equation, we'll just call it dx plus ey equals f, where this is also in standard form. The thing with systems of equations, however, just is simply this. We talk about, so what would we consider a solution to a system of equations? Well, here's what we know in general. A solution to an equation would be some point xy, okay? That when we plug it back into the equation, we would get a valid or a true statement. We would say it satisfies the equation. It's just that now that we're dealing with an entire system of equations, we can't just find a point that would say necessarily that when we plug it back into the first equation, it makes it happy, or when we plug it back into the second equation, it makes it happy. It has to satisfy the entire set of equations here. So we are now looking for a solution to a system, which means we're looking for a point xy that would satisfy every equation in the system simultaneously at the same time. So what we'll do is we'll start by acknowledging this. We say a solution to a system of equations, a solution to a system of linear equations, okay, they're lines, in two variables is an ordered pair xy at some point xy that satisfies each equation in the system. And that's going to be what we're primarily concerned with, because these equations, eventually we'll set up situations in which these equations represent a certain context, and we want to make several different things true simultaneously. Okay. So let's go ahead and start by having this conversation looking down here at this first system here. 3x minus 2y equals 2. This is equation number 1. And then the next equation there, x plus 2y equals 6 is our second equation in our system. What we want to do is we want to find a solution that when we plug it back into both of these, it makes them both true at the same time. So what I've done is I've listed a couple of candidate points down here, candidates, and I want to check to see if these are solutions to the entire system. So all this means is we're just going to take this x and this y and we're going to plug it into the first equation and in the second equation, and if it makes them both true, then we say, look, 2, 2 would be a solution to the system. Now what if we plug it into the first equation and it makes the first equation true, but it doesn't make the second equation true? That would not be a solution to the system, because what we know is a solution to an entire system of equations has to make all of the equations true at the same time. So let's go ahead and take a look at what this would look like here. We say, okay, so the first equation, we'll take out our x and our y, and we'll plug in the point 2, 2. We say 2 in for x, 2 in for y, and this simplifies down into 6 minus 4 equals 2. We get 2 equals 2. This definitely satisfies the first equation. So wait, does that mean that 2, 2 is a solution to this system? Not yet. We have to check it in the second equation. Okay. So checking this in the second equation now, we have x plus 2y equals 6. If we plug in a 2 here and a 2 here, we actually get 2, sorry, let me switch colors back here, 2 plus 4 equals 6. So this implies that 6 equals 6, and that definitely works out. So the good news is we would say 2, 2 is a solution to the system. Solution to the system. Why? Because it satisfies all of our equations at the same time. So now I want to check 0, 1. Okay, see if 0, 1 is a solution to the system. Again, we're just going to do the same process. We say 3 times x in the first equation minus 2 times y in the second equation is 2. What if we did plug in 0, 1? 0, comma 1. So we plugged in 0 for x, 1 for y. We say we would get instead 0 minus 2 equals 2. 0 minus 2, well, that's negative 2 equal to positive 2, and that is not true. So this is not, 0, 1 cannot be a solution to the system. The reason why is because it didn't make the first equation true. Now the interesting thing is this. If I were to plug 0, 1 into the second equation, it wouldn't matter whether it made it true or not, because since 0, 1 already struck out, it did not make the first equation true, then it cannot be a solution to the entire system because it would have to make everybody true, and it has already falsified an equation. Okay? So as far as finding a solution to a system goes, that's simply the process right there. One thing I would like to do, however, is this. What if we interpreted this graphically? Okay, so I want to find the solution to this system graphically. Recall that when you graph an equation, so such as 3x minus 2y equals 2, let's say we wanted to graph our system. We say 3x minus 2y equals 2. What would this look like? Okay, so since this is in standard form, we're going to graph this using what we call the intercept method. We'll find where it hits our x and y axes by plugging in 0 and 0 respectively for x and y. So we say x, y. We say plug in 0 for x, 0 for y. So if we plugged in 0 for x, that is plugged in a 0 right here, we'd get 3 times 0, which is 0, and we'd be left with minus 2y equal to 2. In other words, y would equal negative 1. So we know this hits our y-axis. We've got the point 0, negative 1 as a solution pair. We've got to shade that in. So now, what if we plugged in 0 for y? We'd get 3x minus 2 times 0 equals 2. In other words, 3x equals 2 and x equals 2/3. So when y is 0, we get 2/3 for x. So we'd go over about 2/3 on our x-axis and we'd say right there. And here's our equation number 1. All we've done was graph this line in standard form. The important thing to note here, though, is this. This is 3x. 3x minus 2y is 2. The important thing to note here is this. When you graph an equation, what this entire line is doing is it's shading in all the points that are solutions to this equation. All the points that are solutions to this equation. Now keep in mind, with this system over here on the left, we were looking for a common solution between them. Like the point 2, 2 was a common solution for both of them. What this means is then, when we graph this second equation, the point 2, 2 should also be on its graph because it satisfied it as well. So what if we did graph x plus 2y equals 6? So we say, okay, so x plus 2y equals 6. We're going to do this a little bit quicker this time with some mental math, but what if we did plug in 0 for x? If 0 was plugged in for x, this would be gone and we'd have 2y equals 6, so y would be 3. So in other words, it hits our y-axis up here at 3. 1, 2, 3, there it is. Okay, and if we plugged in 0 now for y, we get 2 times 0. Oh, sorry, I was thinking of 2 there. 2 times 0, this would go away, and x equals 6. Okay, so it hits our x-axis at 1, 2, 3, 4, 5, 6 out here. So I say when I connect these dots, and this is going to be very, very kind of a poor graph. We're going to graph it with a graphing utility here in a second. We should label this, I'm going to label it with EQ2 in our system. But the bottom line is this. You notice right here at 2, 2 is where our graphs intersected. So graphically speaking, when we are looking for the solution to a system, what we're really looking for is any point at which our graphs intersect, because where they intersect would necessarily be a common solution point, and that's what we want. We want a solution that they both share. Okay, so let's go ahead and take a look at what this would look like in a graphing utility here. Put my pen down and we'll go take a look at it. We had these two equations. We had 3x minus 2y equal to 2. There was our first equation that we had graphed, and we had x plus 2y equal to 6. Oops, x plus. Let me fix that. Plus 2y equal to 6. And so what I want everybody to see here is this. When you graph these, of course, the graphs are showing all the solutions to each individual equation, but they have one, and specifically one solution that they both had on their graphs, or where they intersected, and that was the point 2, 2. Okay, so here's what I'd like to do. I'd like to go back over to here and say, okay, well, we'll kind of block all this off now. I have this second system right up here, and what I want to do is I want to solve this system. But the method for us solving systems, we're going to do this both graphically and algebraically, but a really nice method is to just go ahead and graph these lines and see where they intersect. So we're going to do this first by hand, and then we're going to do this over in GeoGebra, our graphing utility, just to show you that doing this graphically is nice, but it's not necessarily the most accurate way to do it. So we say, okay, so graphing our first equation here, let's find where it hits the y-axis by plugging in 0 for x. So if we plug in 0 for x, we get negative 3y equals 6 Therefore, y must be negative 2 when x is 0. So we say negative 2 on our y-axis, negative 2, and we'll draw a dot right there. Where does it hit our x-axis? So we'll plug in 0 for y, which causes that to cancel out. We would get 2x equal to 6, so x would be 3 when y is 0. So if y is 0, we get 3 on our x, 1, 2, 3. Whoops. Let's undo that. It's not what I wanted. I must have clicked on zoom. Apologize. Let me kind of fix our screen here real quick. That's better. Okay. So we were going over 3 on our x-axis here and drawing in a dot. So we say here's all the solutions to equation number 1. This is EQ number 1 that we've got listed up there. So now graphing EQ number 2, we say when we plug in 0 for x and that goes away, we have y is negative 5. Okay, so we'll go down to negative 5 on our y-axis. 1, 2, 3, 4, 5. Draw in our dot, our y-intercept. And to find where it hits the x-axis, we'll plug in 0 for y. So we get negative 4x equals negative 5. If we divided both sides of this by negative 4, we would get x equals positive 5/4 because a negative over a negative is a positive. So that's about 1 1/4. It is exactly 1 1/4. I'm going to get all this stuff out of the way. So it hits our x-axis over 1 1/4, basically. 1 1/4, that's about right here. So we say, okay, so what is the solution to this system? Is there a solution that exists? And it would have to be this point right here. And so if I had to guess at this, I would say this is about over 1 down 2. Now I can't be certain, but just as we did in the beginning, we said check to see if it's a solution to the system. Well, check to see if it's a solution just means plug it back in. The only stipulation here is that we got to plug it back into both. So we're going to plug this back into the first equation first. We get 2 times x minus 3 times y is 6. We're plugging in 1 comma negative 2. So we get 2 plus 6 equals 6. 8 equals 6. And that is definitely not true. So 1 negative 2 is not, I repeat, not a solution to this system. So what's wrong with this? What's wrong with it is we didn't use graph paper. So what I want people to see is, first of all, if we're going to solve a system by graphing, you need to be using a graphing utility or graphing paper to be very, very accurate. Solving by graphing is not an accurate system of solving a system. It's not an accurate method for solving a system. So 2x minus 3y equals 6. There was our first graph. Our second graph was, negative 4x plus y equal to negative 5. There it was. Okay. So we have 2x minus 3y equals 6. Negative 4x plus y equals negative 5. Our solution would be this point right here. Okay. And so in this case, it seems that I've come up with a couple of equations that weren't very, very pretty, which is not really what I wanted to do. But basically, this is the method for solving a system of equations. One method is the graphing method, would be to graph them both and to look for this point. And it seems in this case, if you look up over here, the point would be 9/10, comma, negative 1.4, negative 1 4/10, which we will be able to find once we start, exploring algebraic methods for solving this system.